Welcome everyone, and today we are very happy to have Ying telling us about a quantum circuit interpretation of evaporating black hole geometry. So take it away, Ying.
Okay, thank you, Shuheng. Hello, everyone, and thank you for letting me speak here. I hope everyone stays safe and healthy. Today, I will talk about a quantum circuit interpretation of evaporating black hole geometry. And it's based on recent work, and it uses some idea from another work earlier. So first, the outline of the talk. I will explore the idea that different kinds of gates are stored in different regions of space-time. I think at this point, this sentence probably does not make sense for most of you, and I will try to explain later. And I will try to explain it by various examples. Two-sided black holes, one-sided black holes, and I will try to define what I mean by two-sided and one-sided black hole carefully. In particular, I don't mean counting the number of boundaries. And we will look at the example of a transition from a two-sided black hole to one-sided black hole. Then we will look at apply these ideas to study the evaporating black hole geometry. So first, bulk tensor network and quantum circuit. From this set of earlier work, we learned that the bulk geometry reflects the minimal quantum circuit preparing the state. This picture is from this paper by Lenny Saskin. The left side shows a quantum circuit representing thermal field double. So we represent thermal field double by S-Bell pairs. The black lines here represent qubit. So 1, 2, 3. So it's a five Bell pairs. Each side has 5 qubits, and the time goes up. The red lines here represent quantum gate. So this particular line segment represent a 2 qubit gate. So a gate coupled these 2 qubits. Then another gate, a gate, a gate, a gate. So the black hole dynamics is modeled by a quantum circuit like this. As time goes up, as time increases, the quantum circuit gets longer. In the red panel, we basically pull up this circuit and we lay it here horizontally. And as time increases, this quantum circuit gets longer. Correspondingly, the black hole geometry, if you want to look at the black hole geometry, the wormhole gets longer. So the wormhole, the lengthening of the wormhole reflects the fact that the quantum circuit preparing the states is getting longer. That's the interpretation of these two pictures.
Excuse me, Ying?
Yeah. Yeah.
The time on your left-hand picture, you have time going up in both directions.
Yes.
Filling time in the black hole geometry picture.
Yes.
Goes opposite directions on two sides. So can you tell us the connection between the time parameters on the two sides?
So let's say start from t equals 0. It's a bunch of Bell pairs. Then t goes this way, t goes this way, t goes this way. Let's say at a particular, let's say TL equals TR equals T. This is a quantum circuit. At TL equals TR equals T, there is a long wormhole here.
Okay. So the time is on, say, the left-hand side is going backwards to the killing time.
Yes. It's opposite to the killing time because of the killing symmetry. If I do the time evolution in the opposite direction on both sides, then nothing happens to the state.
That's what I thought. I wanted to make sure.
Okay, so yeah, it's the left-hand side, the time. So in this talk, I will allow, say, both time to go up. The left time is opposite to normally the killing time people talk about. Okay. So this is one particular example. It's a one-sided black hole. It's a pure state black hole. As we apply unitary time evolution to the circuit, the state gets more complex and the minimal circuit gets longer. And one can see that as time increases, the Einstein-Rosen bridge also gets longer. Here I draw the maximal volume surface. As time increases, the wormhole is getting longer. And for this particular set of simple examples, one can identify circuit time with boundary time. It's because of this kind of boost symmetry here. The amount of time increase here equals to, if you write it out in Schwarzschild coordinates, there is a horizontal time. The amount of time increase here equals to amount of time increase here. I mean, the exact identification doesn't matter. I mean, in this picture, I draw light-like lines. In this picture, I draw maximal surface. The point is the amount of increase here is the same as here. So in some sense, the circuit time is identified with the boundary time. And of course, normally when people talk about circuit time, quantum circuit has discrete time. We identify d tau here equals 2 pi over beta dt, where beta is the temperature, is the inverse temperature of the black hole. In order to motivate the main idea I will need to use in this talk, let's do a small digression. Let's talk about uncomplexity. I mean, I won't need to use uncomplexity in the rest of the talk, but hopefully to give some motivation about, say, why we say different kinds of gates are stored in different space-time region. Uncomplexity, it's as its name suggests, it's the opposite of complexity. It characterizes how simple a state is. To be more specific, it quantifies the computational power of a particular state. Uncomplexity of a pure state, the definition was given in this paper. It's given by the maximal possible complexity of this state minus the current state complexity. And just like complexity of a state, uncomplexity, one can also give it some geometric meaning. As we mentioned before, as the wormhole gets longer, the complexity of the state increases. There's another way to say it. I mean, as the wormhole gets longer, we say that the uncomplexity decreases. So we can say that the growth of the wormhole actually consumes uncomplexity. It consumes the computational power of the state. In some sense, the growth of the wormhole is fueled by uncomplexity of the state.
Sorry, Ying, a question about the last.
Yes.
If I start with some psi and maximize over all u, isn't the maximum always the same? Like.
Yes, it's a constant.
Okay, so the
I
first
just mean maximal complexity.
Okay, so it's just basically some constant minus the complexity of the state.
Yes.
Okay, thanks.
I write it in this way to compare with the mixed state case in the next slides.
Okay, thanks.
Now we want to generalize this set of ideas, this set of complexity or uncomplex to mixed state. We immediately encounter a question here. Let's say we have a density matrix rho. One can apply unitary operators U to this rho. Let's say rho is mapped to U, rho, U dagger. But the problem is not all unitary U can affect the density matrix rho. There is a large set of U that does not change the density matrix rho. We need to identify those operators and treat them separately. Another difficulty involved in this is for a density matrix rho, it has different purifications. So it's hard to talk about complexity of a density matrix as for which purifications shall we choose. But as for uncomplexity, it's one expect the computational power of a density matrix does not depend on the purification we have. So let's ask the question this way. Say Alice has a density matrix rho A and Bob has subsystem B. Together, they are in a pure state psi. So psi is a purification of this density matrix rho A. Let's ask, how much computational power can Alice get out of the state psi when she only has subsystem A. And we define this computational power as the uncomplexity of the density matrix. The definition was given in an earlier paper. It's given by the maximal complexity this psi can reach by applying unitaries on subsystem A minus the maximal complexity this psi can reach by applying unitaries on A, but we require that these U do not change the density matrix rho A. The key point in this definition is that we need to exclude those unitaries that make the state more complex, but actually do not change the density matrix. I mean, there are a set of unitaries that make the state more complex, but it's included here. But some of them do not change the density matrix. It's included here. So we see that these sets of U's are not included when we consider the uncomplexity of the density matrix. I mean, these sets of unitaries that can make the overall state more complex but do not change the density matrix, they are special. And later we will see that they play a special role in holographic state, and we will treat them separately. And they do not contribute to the uncomplexity of this density matrix. But first, let's ask, what kind of unitary operators are they that they somehow make the state more complex, but they do not change the density matrix? Here's the claim. If the unitary operator does not change the density matrix, then it can be undone by some other unitary on B. We again assume A and B are, say, entangled. So there exists UB such that UA acting on psi equals UB acting on psi. It's easiest to see if we look at the Schmidt basis. Let's write out the density matrix rho A in Schmidt basis. It has a block diagonal form. It's a, let's say it has some, it's a diagonal matrix. Let's say it has some eigenvalues lambda 1, some eigenvalues lambda 2, lambda k, and some eigenvalues 0. Pictorially, we represent a shared eigenvalue by a line. It's say 1 eigenvalue lambda 1, 3 lambda 2, 4 lambda 3, and some 0. When it has eigenvalue 0, then this part, they are just not entangled. Once the density matrix rho A is in this form, it's clear to see that what are the unitaries that do not change the density matrix. We need to look for those unitaries that commute with this density matrix. They are block diagonal as U of N1 times SU N2, SU NK to SU N0. So what are they? They are exactly those relative Schmidt basis rotations. So you can do relative rotations here. For these relative Schmidt basis rotations, let's say if we apply such a U on A, then it can be undone from subsystem B. So those special unitaries those unitaries that potentially make the state more complex but doesn't change the density matrix are the unitaries that can be undone from the other side. So here's the end of the digression. What we learned from it.
Question?
Yeah. Yes.
So does this uncomplexity of a mixed state depend on both rho and psi on the previous slide?
The reason I define uncomplexity this way, yes, the definition depends on psi, but the form depends on psi. But one expects the computational power does not depend on the purification.
But does the actual number, this definition of the uncomplexity, will depend on psi or not?
I expect it doesn't depend on psi.
Okay.
What we learn from this is that there are two kinds of operations Alice can apply. Let's say when she has a shared, when she has her subsystem that's entangled with the subsystem B. The first kind of operations are those relative Schmidt basis rotations between the two subsystems A and B. These operations can be undone from side B, and of course can be undone from side A. they belong to either, they do not belong to either side alone. This kind of operations only make sense when you have both subsystems together. If you just have one subsystem, it doesn't make any sense. The second kind of operations are the opposite of this. It's there are unitary operators you can apply from subsystem A that cannot be undone from side B. It actually changes the density matrix row A, and it makes sense for row A. There is a relation of this to subregion duality. Let's look at this Penrose diagram. We have subsystem A, subsystem B represented by two boundaries. And the blue dot represent the RT surface. The orange region is the entanglement region. It's outside the entanglement wedge of either subsystem A and B. We want to say the first kind of gates are responsible for the growth of the orange region. So because the first kind of gates makes no sense for either subsystem A and B, it only makes sense for the union of these two. And we say the first kind of gates is stored in this region. I mean, in this talk, when we say that some gates are stored in some region, what we really mean is that the growth of a certain space-time region accompanies the growth of certain parts of quantum circuit. We mentioned before, there is a minimal circuit that's responsible for the growth of this wormhole, but there are different kinds of gates in the circuit. There are gates belonging to, say, the first kind of gates that can be undone from both sides. If this part of circuit gets longer, then this region grows. And if the second part of the gates, if you apply second kind of a gates, let's say if this part of circuit gets longer, then the red region grows. That those operators can be undone from side A, but cannot be undone from side B. We say that the first kinds of gates are stored in orange region, while the second kind of gates are stored in the red region.
I have a question.
Yeah.
So if we go back to the previous transparency.
Yeah.
This idea that whether they can be done or undone, is it supposed to be an approximate or exact statement? The reason I'm asking is because I mean, in principle, in the thermal field double, if there are no degeneracies, right?
Yeah.
The only kinds of gates you have of this kind that can be undone from one or the other would be like pure phases.
Yeah.
And they are somehow time evolution by some amount.
Yeah.
So are you imagining that are the, I mean, those are the gates that we are allowing the orange region? Because if it is just exactly the time evolution, it sounds like it cannot be something simple. I mean, it cannot be a simple gate made out of simple parts, because you have to make act with the full Hamiltonian. Well, okay, maybe.
Yeah. I see what you mean. I mean, later I will say check this statement by examples, but in an example, it's always a simple toy model that the black hole time evolution is represented. The black hole is considered as just S qubits, and in that case, the black hole time evolution is considered as the unitary, all possible unitaries on this S qubits. But I would say that's actually approximation to the true Hamiltonian time evolution. The true Hamiltonian time evolution, because the density matrix is thermal e to the minus beta h, and the true Hamiltonian evolution acts on infinite number of qubits. And if we say that somehow we represent the black hole by say S qubits, and that Hamiltonian evolution is considered a random unitary on this S qubits, there is already approximation there.
Okay, so this somehow, in this idea, we are ignoring the fine details of the energy levels.
Yes.
Okay, good.
And I would say, I think this set of ideas should be approximate, just because Yeah, just because the idea that say black holes are composed of say s qubits and the unitaries on them, just the Hamiltonian evolution unitary on these s gates, there are already, this set of ideas is already approximate.
Sorry, Ying, what's happening in the white regions? There is no gate.
The white region is time independent. That's exterior.
Right, but the circuit is there as well, right?
Yeah, but when we say the black hole is composed of s qubits, we somehow already look at the black hole when we stand here.
Somehow you're only interested in the regions behind the horizon.
Horizon, yes. When we say it's composed of s qubits, we already stand here.
Okay, thanks.
Let's look at the simplest examples, two-sided black hole, thermal field double. Let's say we represent thermal field double by s-bell pairs. I mean, I think this is already approximation, the true, yeah, the corresponding wormhole geometry has minimal length. So if we look at the corresponding wormhole geometry, you see that they, the two event horizons actually meet here. Now we do time evolution. We can apply some gates, which is well represented by these orange dots. We can apply gates from either side A or side B. These gates can be undone from either side. They do not belong to subsystem A or B alone. Why? Because, for example, from subsystem A, you can see that there are gates here, but the gates can be undone by subsystem B without A knowing it. So this gate makes no sense for subsystem A. If we look at the wormhole gets longer, but the part that actually gets longer is outside A's entanglement wedge, and it's also outside B's entanglement wedge. The parts that growing is in an entanglement region, which again makes no sense for A and B alone. It only exists when you have a union of A and B by the miracle of ER equals EPR. Let's briefly pause here and compare one-sided and two-sided black holes. Let's say what we mean by one-sided and two-sided black hole. For two-sided black hole, when Alice has a two-sided black hole, the interior is outside her entanglement wedge. So Alice cannot predict the infalling observer's experience. When she sends in a kitty into the black hole, the kitty can either meet a flower or a bullet sent in by Bob. From a point of view of quantum circuit, the expansion of the interior does not consume Alice on complexity. The expansion of the interior is fueled by those relative Schmidt basis rotations between these two. It does not consume Alice on complexity. As the quantum circuits get longer, there are more gates laid down on the circuit. But the gates in the circuit does not change Alice density matrix. The growth of the wormhole does not consume Alice on complexity. This is two-sided black hole. Let's look at one-sided black hole. When Alice has a one-sided black hole, she can predict the infalling observer's experience because the interior just is inside her own entanglement wedge. In principle, she knows everything about what's inside. From a point of view of quantum circuit, the expansion of the interior is fueled by Alice on complexity. Let's say as the interior gets longer, the complexity of state increases and the uncomplexity of state decreases. In this talk, when we say that Alice has a one-sided black hole, what we mean is just the properties we just mentioned. What we mean is that the interior region accessible to her is determined by her subsystem. She can, in principle, predict the infalling observer's experience. I mean, because we use this term, one-sided and two-sided, in such flexible way, the property of a black hole being one-sided or two-sided can be a time-dependent property. I mean, we do not mean counting the number of boundaries. In particular, for example, like this, let's say the RT surface is deep in Alice interior, we would say Alice black hole is effectively one-sided because when she jumps in, she just stays in her own entanglement wedge.
It is equivalent to saying whether the near sort of interior region is in the entanglement wedge or not.
What do you mean by near interior region? You mean this part?
Well, the region that you access when you fall in.
I think so. I think so. I think it's, I would say it's equivalent in the quantum circuit statement that say the growth of this, the growth of the interior is consume her own complexity.
Okay. I mean, the point I was making is I mean, this whole business of entanglement wedge is something we can define precisely, right?
Yes.
So with entanglement wedge, we can decide where the interior is and what.
I think so. I agree. I simply want to make a connection between this set of ideas and the idea from complexity that some gates, there are circuits in the interior, but there are different kinds of gates, and some gates are different. Right. Yeah, different kinds of gates in different regions. Yes.
Can we say what you're saying as saying that the region that is in the entanglement wedge will be the gates that will not be undone? Which
yes, exactly. That's exactly what I want to say, or what I said. Okay.
Fine.
Yeah. Thank you.
Not in any of the two is the part that can be undone.
Yes.
Very good.
Yeah. Thank you. Thank you. That's exactly what I thought I said. Probably I didn't say it clearly. So let's look at one more complicated example, the transition from two-sided to one-sided black holes. This is actually a rather familiar example. I just want to give it some different interpretations. So, it's studied in a paper by Shankar and Stanford. Let's say we start from thermal field double and say we throw in extra photon from Alice side at some time TW. These authors find that there will be significant backcorrection on the geometry after scrambling time. If you wait for scrambling time, the wormhole gets significantly longer. Here is a quantum circuit picture of this setup. Let's say we start from thermal field double. So we start from A and B connected by S-bell pairs. And there are a bunch of orange gates. The orange gates can be down or undone from either side. And then an extra qubit come into Alice side, extra qubit come in. It affects more and more qubits. And when you wait for scrambling time, it can affect the entire system. Any gates that are affected by this extra qubit cannot be undone by Bob. Why? Because it involves these extra qubits, but Bob has no access to the extra qubits. So in this picture, the red gates can be undone by Alice, but not by Bob. We want to compare quantum circuit.
So you're imagining that Alice does have access to those extra qubits?
Yes, this extra qubit belong to Alice. Let's say there are 1, 2, 3, 4, 5, 6. There are 6 lines here. There's supposed to be 1 more lines here. Yeah, 7 lines here. Alice has access to this extra guy.
Okay.
I mean, as Wang just mentioned, I mean, the idea is different kinds of gates are stored in different regions, space-time region. So what we want to say is that those orange gates are stored in this orange region, and the red gates are stored in this red region. What's the difference? Because let's say this is RT surface. The orange region is the entanglement region. It's a region which only makes sense where you have both subsystem A and B. But the red region is inside Alice entanglement wedge. We want to say that these red gates are stored here. And we will make the more quantitative comparison. To make more quantitative comparison, let's introduce a toy model of the growth of this operator, an epidemic model. So we model the black hole dynamics by a Hayden-Prescott type random circuit. Roughly speaking, we have capital K number of, total number of capital K number in this, I guess, 1, 7. Capital K number of qubits. And at each time step, discrete time step 1, 2, 3, 4. At each time step, we randomly pair them up into k/2 pairs. And then on each pair, we apply a randomly chosen 2-qubit gate, a gate here, a gate here, randomly chosen 2-qubit gate. And this perturbation is modeled by an extra qubit coming in here. We imagine this extra qubit as as carrying some epidemic. I mean, at the first time step, it affects one other qubit. Second time step, it affects in total of 4 qubits, then maybe 8 qubits. As you can imagine, the number of qubits affected by this epidemic will grow exponentially in time until saturation. We define a quantity we call size. Size of the operator is defined by the number of qubits that are affected by this epidemic. It's a time-dependent quantity. At this time, it's 1, 2, 3, 4, 4. The size is 4 here, size is 2 here, size is 1 here. And just from this simple toy model, one imagine that the rate of change of this operator first is proportional to the number of sick guys, the number of the number of the qubits that has been contaminated. It's also proportional to the number of healthy qubits left. And here's we impose the initial conditions that the initial size is 1, and then we get how the size depends on the time. We see that when tau is less than log k, it essentially grows exponentially in time. When tau is bigger than log k, it actually saturates. It saturates to s equals k plus 1, the total number of qubits. Our initial goal is what we want to know is the number of gates that say can be undone by Alice, but cannot be undone by Bob. We see that we need to ask what are the number of red gates and what are the number of orange gates. In particular, let's ask how does the number of red gates depend on time? We see that after one time step, the increase of the number of red gates is proportional to the number of sick qubits at this time. Let's say if we count this gate by 2, this gate by 2, then actually we say that after the time step 2, we have 4 more gates which correspond to 4 sick qubits at this time. So the rate of change of the gates that cannot be undone by Bob is equal to the size of the epidemic. The rate of change of the gates that can be undone from both sides is the complement of this, is k minus s of tau. This is a toy model we will use to compare with the black hole geometry. On the black hole side, we want to ask how the volume of this orange region and how the volume of this red region depend on time. So we just ask, let's say we increase this left time by delta t. We ask how much volume increases in this region and how much volume increases in this region. This is a simple calculation in BTZ geometry. In order to compare,
Ying, by volume, you mean volume of some codimension 1 slice that goes through those regions, right?
Good question. Actually, in this case, I directly computed the space-time volume, but I would expect the any quantities reasonably defined, like say action or codimensional one surface, area of codimensional surface would behave the same way. Let's say in a minute, you will see the result. I mean, at least what really matters are just some key features of the time dependence. They all behave the same way. Okay. In this case, for the convenience of calculation, I directly look at the space-time volume. Okay. In order to compare the circuit picture with the black hole geometry, we need to say first identify the circuit time with black hole time. As we mentioned, that d tau is equal to 2 pi over beta dt. So we identify tau as 2 pi over beta times t minus tw. We identify black hole entropy S with the number of qubits k. And here is the black hole calculation result, the rate of volume change of the entanglement region, of the rate of volume change of the orange region, and the rate of volume change of the red region. This is the rate of change of the number of gates that can be undone from either side, the orange gates, red gates. I will just show you the plot. I just randomly pick up a number, log k equals 11. This doesn't mean anything, just randomly chosen. The blue line is represent the increase of space-time volume in Alice entanglement wedge every thermal time. The pink line represents the increase of number of gates that cannot be undone by Bob every discrete circuit time step. And this is the ratio of these two. Then I pick another number of k, log k is 175. I think on computer, you should be able to see there are actually two lines here. Again, the blue line and the pink line, and here's the ratio of these two. We see that other than window around scrambling time, these two actually have pretty good match. And as Raghu just mentioned, it's you have different choice you can use action, or you can use space-time volume, or you can use spatial volume. I expect that they all have the same key features like this. Let's say initially there's exponential growth, and then there is saturation after scrambling time. Because they share the same set of key features, they behave the same way. That's why you see the good match in the plot. So this is the conclusion we draw. It's what Wang actually pointed out earlier, that different kinds of gates Alice can apply are responsible for the growth of different parts of space-time. What I also find interesting is that let's look at the example, not from point of view of Alice. Let's look at the example from point of view of Bob. What do we expect from quantum circuit analysis? We expect that Bob can undo these orange gates, but we don't expect that Bob can undo these red gates. Actually, we expect Bob cannot do anything about these red gates. I mean, by unitary evolution, he cannot do anything about these red gates. Let's look at how his volume changes as a function of his time. Let's look at how the orange region, the volume of orange region changes as his function as a function of his time. The rate of the volume of the rate of change of this volume is proportional to S minus the size of the epidemic. Recall that what's the S minus size of the epidemic? I mean, we mentioned earlier that the size of the epidemic is actually the increase of the red gates at a particular instant of time. So S minus the size of epidemic is nothing but the number of orange gates at a particular instant of time. So what we say is, let's say if we increase time from t to delta t, the number, the volume increase is proportional to the number of orange gates in one time step. So roughly speaking, if you look at time increase in this direction, then it matches the circuit in this direction. I find this interesting. So Bob can only undo the orange gates in the circuit. And actually, if you go back, you start from time minus TW. If you go back for scrambling time, and when Bob changes his time, the volume of this orange region no longer changes. That means you hit this boundary. Let's look at another example in SYK and JT gravity. In SYK, one can do a better estimate of the size. Let's say Alice applies, let's say we start from a low temperature state, which corresponds to, let's say, a black hole. And Alice applies a precursor, U psi 1, U dagger. the size of such a precursor was given by Qi and Stryker in a beautiful paper. Roughly speaking, before scrambling time, it grows as a cinch square. After scrambling time, there will be saturation. From the size, we can estimate its complexity. And actually, in this case, we expect that the size has the same functional form as the complexity in terms of time dependence. Why? Because the growth of this operator forms a tree. And the size counts the number of leaves in the last layer of the tree. The complexity of this operator counts the total number of leaves in a tree. But you know that for a tree, the number of leaves in the last layer grows the same way as the total number of leaves in a tree. That's why we expect it has the same time dependence before scrambling time. Let's compare this result with the geometry calculation. So here I just draw part of ADS2 geometry. This is the RT surface. This is the actual trajectory. I mean, there is a perturbation, and this is actual trajectory, the solid black line. And this line is the trajectory, would be trajectory if the perturbation doesn't come in. If the perturbation doesn't come in, the boundary will follow this trajectory. So, and then the horizon, this would be the horizon if there's no perturbation. And after this perturbation comes in, the trajectory actually deviate, goes this way. We look at how the volume changes as a function of time. Here's this is just some simple calculations done in JT gravity, and one can see that the function goes like log of 1 plus a small factor sinh square. We see that before scrambling time, they essentially have the same time dependence. And after scrambling time, we expect size saturate and the complexity start to grow linear in time. And this guy indeed grows linearly in time after scrambling time. So what we learn is that the growth of Alice entanglement wedge is due to those computations involving psi 1 of t, involving these actual perturbations. And these computations, because they involve this actual perturbation, they cannot be undone by the other side. They are responsible for the growth of this entanglement wedge. A brief summary here. Let's say we have a two-sided black hole, A and B here. There are two boundaries, A and B here. This is the RT surface. The orange region is entanglement region. What's stored here are the gates. So there is a quantum circuit stored in this interior. But inside this quantum circuits, there are different kinds of gates. There are gates that can be undone from both sides. They are stored in this orange region. And they are essentially the relative Schmidt basis rotations. And there are gates that can be undone by Alice, but cannot be undone by Bob. They are stored in this red region inside Alice entanglement wedge. Are there any questions before I move on to evaporating black hole? Let's look at the evaporating black hole. There was significant progress last year on the understanding of evaporating black hole. There was these are the two papers came out in May. These authors find that after page time, there will be a new RT surface such that most of the interior belongs to the entanglement wedge of the radiation. And here we will look at this geometry from a point of view of quantum circuit. And here are the questions we want to answer. First, why is it that around page time, adding a few more qubits to the radiation give rise to a very big jump in the size of the region contained in its entanglement wedge? The second question is, why does the bulk region belonging to the radiation, I mean the island, keep growing after page time, while the radiation itself actually doesn't do any computations? Because the radiation, when it's leave the black hole, it's just freely streaming, it doesn't do any computations. Here is the circuit. We draw the circuit around page time. Around page time, we expect the black hole is maximally entangled with the radiation. So let's explain the circuit. Let's say we start from initial state, time increases this way. And as time increases, more and more qubits coming out as radiations. And here, this part is the remaining black hole. At around page time, the black hole is maximally entangled with radiation. Because, I mean, this is the assumption here. This in realistic situation is probably not exactly true, but let's make this assumption in this very crude circuit model, see what does it predict. Then because the black hole is maximally entangled with the radiation, and there is a circuit connecting them, and all these gates can be undone from both sides. That's why I draw them as orange. All these gates can be undone from the radiation, and it can be undone from the black hole side. Here, I draw the same picture, just in a different way to make the situation more clear. The point is there is a circuit connecting these two guys, and all the gates can be undone from both sides. There is supposed to be a Python's launch in the middle that I didn't draw, because our focus would be on this end of the circuit, actually for scrambling time. Our focus will be here. And because the evaporation is slow, so this circuit locally just looks like this circuit locally. Also, for the convenience of the discussion, I will assume Alice has the radiation, while Bob has the remaining black hole. Let's say our assumption is here. The remaining black hole, after page time, the remaining black hole is maximally entangled with the radiation. And what does this imply? This implies Bob has a black hole. The black hole is doing computation, but all the computations can be undone by Alice. This implies Bob doesn't have his own computations. He can keep doing computation, but all those gates laid here can be undone by Alice. So essentially, he has a two-sided black hole. I mean, there is an interior there, but the interior is shared with Alice. He doesn't have his own interior. The claim is this will imply the RT surface lies at the horizon. I will first explain why. Because let's say if the RT surface lies inside the horizon, then as time increases, this part of the space-time, this part of interior will belong to Bob. But we said Bob doesn't have his own gates. I mean, he applied a lot of gates there, but all these gates can be undone by Alice. So he doesn't have his own gates, so the RT surface cannot be inside. What if the RT surface is outside? The RT surface is outside implies that not all gates not all qubits are doing computations. That means if the RT surface is outside, that means Bob has more qubits. The remaining black hole has more qubits than those qubits are doing computations. So this very crude circuit model would imply that the RT surface lies at the horizon. But the two papers last year actually shows that the RT surface lies slightly inside the horizon. This because this assumption is not exactly true. We assume the remaining black hole is maximally entangled with the radiation, but in fact, it's not exactly entangled with the radiation. That's why Bob still has a tiny portion of the interior. But if this is a reasonable assumption, then at least the RT surface will be very close to the horizon. And indeed, what those people find from the two papers last year is that the area of this surface comparing with the area of a horizon, the difference is of order. It's just the difference in the area is a couple of Planckian area. let's see the appearance of island. Let's see what happens after page time. After page time, let's look at one time step. In one time step, Bob, who has the black hole, gives C qubits to Alice, who has the radiation. Let's see what these C qubits do in the circuit. And at this time, we start from a circuit connecting the radiation and the black hole, and all the gates are orange. And then the C qubits go from Alice to the radiation. Let's trace what the C qubits do in the circuit. We read the circuit from right to left. We read the circuit in this way. These C qubits will get scrambled because this is a scrambling circuit. These C qubits will get scrambled. It will affect more and more qubits. After, if you go back for scrambling time, it will affect the entire system. And any gates at the left of that, all of a sudden turn red. And when they turn red, they belong to Alice. I mean, before everything is orange, are shared from both sides. But now, if you go back for scrambling time, any gates here turn red and they belong to Alice. And also, because we are looking at this portion of circuit who does the scrambling time here is given by beta over 2 pi log S over C, where S is the entropy of the black hole at this time. And C is the number of species in the Hawking radiation, is the central charge of the bulk quantum field, is the number of species in the radiation. And as we mentioned before, the red gates cannot be undone by Bob, but they can be undone by Alice. They belong to Alice. Here, I just draw the same picture in a slightly different way to make a comparison with earlier discussion of perturbed thermal field double. We start from a circuit connecting radiation and black hole. All the gates have color orange. And when the black hole somehow gives C qubits to the radiation, then if you go back for scrambling time, all the gates turn red and then they belong to Alice. We see that Alice gets her own share of gates, even though all the computations were done by Bob. And the red gates from the island. The red gates are interior of Alice one-sided black hole. And let's see what does this imply about the evaporating black hole geometry. We see that the circuit stored in the interior takes scrambling time, where the scrambling time here is beta over 2 pi log S over C, to scramble the C qubits. This implies any gates apply scrambling time earlier, the circuit time, here I mean circuit time, any gates applied circuit time, scrambling time earlier can no longer be undone by Bob. So let's say this is the current time. If you go back scrambling time earlier, all the gates turn red. They can be no longer be undone by Bob. And this implies that the RT surface is scrambling time behind the current time because the horizontal circuit time here matches the boundary time. So if you go back for this amount of a time, all the gates turn red and they belong to Alice. This will be the last slide of my talk. Let's see when the black hole itself.
I have a question.
Yes.
So if you go to the previous slide, or actually the slide before that.
This one.
This one, yeah. So in between where we have both orange and red, so in the region between the two dashed lines.
Yeah.
If I make a vertical slice, some of the slices have part red, part orange, right?
Yeah.
Is that part red, part orange captured somewhere on the next figure? Because there we have pure red or pure orange, like, so especially in the figure on the right. So that circuit is supposed to be on this slice, right?
Yes, roughly speaking. And to answer your question, the reason is no. This crude circuit model does not characterize, say, this part. The reason is so what this picture says is that even before scrambling time, there are some gates that already belongs to the radiation that cannot be undone by the black hole, right?
Yes.
And if you look at this picture, I believe what happens is that, during this time, there are radiations coming out.
Mm-hmm.
So there are radiations already coming out from here.
Mm-hmm.
And those radiations, of course, they belong to the radiation, but they are not reflected in this classical geometry.
Okay, so it doesn't capture that amount of that detail.
Yeah, I think the classical geometry here doesn't capture that amount.
Okay.
Thank you, Raghu. It's a good question. The growth of the island. This picture is badly drawn, but let me try to explain. What I mean is I just, let's say we're already after page time. We just see what happens at each thermal time. Let's say one thermal time corresponds to one discrete circuit step. At one time step, what happens first? Bob, who has a black hole, apply roughly S black hole, apply S gates. And there are S new gates that are put here. And Bob also gives the C qubits to the radiation. The assumption here is C much less than S. Because C is much less than S, the loss of C qubits has very little effect for the S gates just applied. And in fact, it has very little effect for the gates one layer before. But the loss of C qubits will be significant if you go back for scrambling time. So what happens is if you go back for scrambling time, there will be a layer of gates which turn from orange to red. So at each thermal time, there is a S gates, the circuit gets longer, S gates are applied here, C qubits are given to the radiation, and one layer of circuit change color from orange to red. We see that Bob has a two-sided black hole, and he does all the computations. So the interior of this two-sided black hole grows at this end of a circuit. But at the same time, there is constant transitions. If you go back for scrambling time, there's constant transitions of the gates. It transitions from orange to color. It goes from being the interior of two-sided black hole to becoming the gates belonging to the radiation, and they become the interior of, say, the radiation. Essentially, it's a radiation controls this part of a circuit, and the radiation has its own interior. It's such constant transition happens, so the island keeps growing. That's basically all I want to say in this talk. Thank you very much.
All right, thank you, Ying. Is there any other question for Ying?
Yeah, I guess if I can maybe follow up on the last question that I asked. So if you go back to that picture.
Okay.
Of the Penrose diagram and the red and orange.
You mean this?
Yeah. So between these two dashed lines, let's look at the picture on the right.
Yeah.
You assigned it the color orange, where there is this curved arrow T star, right?
Yeah, what I mean is even though I assign color orange, because there's constantly radiation coming out, which is not captured by this geometry. And the radiation coming out during this time, that part of the radiation, it's in our 3D model, it's, this part, there is a, yeah, there's a, yeah.
What I was going to ask is, so in the circuit, that region is the thing that's both red and orange, right? So why do we pick the orange color here rather than red?
Because the red color, the red region is significantly less than the, let's say the, how can I?
Well, in, yeah, in this picture.
Yeah, from the circuit picture, you ask me why is it, why? Because if you really work out either the circuit model or the black hole model, you will see that the volume of this, of the number of these orange gates is order S log S. The volume of these red gates is of order s. They are smaller than log s. So
Okay.
it's, yeah.
Okay, thanks.
And the reason is, roughly speaking, is you see that it's the rate of increase before that is essentially very close to zero. I mean, this is the rate of change of the red gates before scrambling time is very close to zero. It's an exponential increase.
Mm-hmm.
And you see that exponential becomes almost a step function if you have a large number of qubits.
Mm-hmm.
Any other question?
So yeah, I guess you're saying if you were to stop the radiation, you decouple the black hole from the radiation, you continue evolving it, then it the island would not grow anymore, right?
Yes. Yes. You mean if we decouple them, then because the radiation is freely streaming, then yes, I believe the island no longer grows.
Right.
All right.
One more question.
Yes,
Yeah.
please.
But it seems like it's not going to grow even if the radiation has some interactions. At least in these.
Let's say this is like if you don't have a black hole, if you just have an ordinary quantum field with small interactions, you can say basically one could say that the, let's say, ordinary weakly coupled quantum field theory, is it doing computations? Yes, but in a rate that's very slow and is not reflected in classical geometry.
Okay. Thanks.
I guess if you collapse the radiation into another black hole, then it
Yes.
will grow.
Mm-hmm.
Yeah, then it will grow. Yeah.
I see.
Any more questions? All right, if not, let's thank Ying again. Thank you for the very nice talk. Thank you.
Thank you.